Hello, testing. Okay, sorry, I was late again. So previously I was, because of FYP, there's no more FYP, but we still do algebra geometry project. So we calculate some very interesting stuff. So that's why I'm late here. Yeah. Right. So for the interesting stuff, you are interested, we got a seminar on next Saturday if you want to come. Full day seminar. Huh? Depends. Okay. Right. Yeah. So where are we? Where we left yesterday? Okay. So yesterday we were discussing about when can we give a topological space metric, okay, such that we don't simply give metric, maybe any metric could work, but we want the metric to induce the same topology, okay? We want to induce the same topology that we started with. Okay, so when can we do that? The claim is every second countable regular space is metrizable. Okay, so that such that when you give a matrix to this space, and it induces the original topological space. Induce the original topology. So yesterday we gave an outline of the proof. So we want to show that it's homeomorphic, okay, to a metrizable space here. Okay, it's not homeomorphic to the whole space R omega here, meaning infinite product of R, but it's just homeomorphic to a subspace of it. Okay, then it's enough. And then we claim that this infinite product space here is metrizable. Okay, and this claim we won't prove it. It's included in your tutorial here. So basically, if you define this metric on your product space, then you consider the open ball is exactly the product topology on this infinite product. Okay. Okay, this part is in the tutorial. So how do we? So now the question is, how should we form this homeomorphism? What's homeomorphism again? Inverse is continuous, right? Continuous function with inverse is continuous. Yeah, very good. So what's the function we need here? So this function here is pretty special. This function here is built up by incountably many functions. Okay, this function is built up by countably many functions. Okay, but how do we get this Fn here? Okay, this is our construction today. Okay, so let's do this. Okay, let's do this. Okay. So note that this Fn here will only map into the closed interval 0 to 1, not to the whole R, just 0 to 1. Okay, and then such that there are few properties here, such that for every open set that contains x naught, then there exists an n such that fnx0 greater than 0, and the complement is 0. Maybe later you will see why this kind of thing is important. Okay, but let's construct this kind of function first. Okay, so how do we construct topological space from how do we construct function from topological space? So remember the last time, yesterday we do Urysohn lemma, right? Okay, but to use Urysohn lemma, we need normal. Okay, but today we have suppose x is X. Suppose X is a second why would not this? Okay, suppose S is a second countable regular space. Okay. Then our example was X is actually a normal space. Okay. This is how you go from regular space to a normal space. You just need second countable. Okay, second countable means you have a countable basis. Okay. I didn't show you the proof. The proof is in your tutorial. You can read about it. So since we got this, then we can use Urysohn lemma. Okay. So we can use Urysohn lemma to find such function. Okay, given x naught and u. Okay, or more precisely, we are looking at the closed set. Closed set use. Okay. Yesterday, Urysohn lemma. What does Urysohn lemma do? We can separate. What can we separate? We can separate two closed set. Okay, but now we are normal, right? Normal is T1. Okay, one point set is also closed. Right, so we can separate S naught and the complement of U, because U is the point. U is an open set that contains X naught. So the complement is a disjoint closed set with S naught. Okay, but if you just simply pick so if you just simply pick a function for each pair here, okay, for each pair X naught and U, okay, how many functions you can pick? What do you think? I got one X naught, I got one U, and then I pick a such F. One S naught, one U, pick a such F. Okay, how many you can do? So yesterday we can send S naught to 1, right? And then close set to 0, right? Okay, so this satisfies this kind of property. 1 is greater than 0. So how many possibility? What do you think? For each S naught and each U that contain X naught. How many possibility? Huh? How many possibility? Huh? What do you think? Counting only. 3? How do you count with number 3? Depend on how many S node you want to pick, right? And then with S node, depend on how many open set containing of it, right? Countably, if S node is uncountably many, if your topological space is uncountably many, then this set of function could be uncountable or more than uncountable. Okay, so in general, this collection won't be countable. Okay, in general, this collection will not be countable. Okay, but just now we said that we want just only countably many of them, right? Okay, so can we cook out just enough to use or not? Okay, let's see if we can use enough function, okay, to describe all these collection of function here. Okay, so what do? We know that something is countable, right? Our space is second countable. Yeah, our space is second countable. So we let Bn be a countable basis here for X. Then what do we have? Okay, so for every nm in n, okay, such that Bn bar is in Bm. Okay. Okay. By Urysohn lemma, we could find a continuous, let's call it G and M here, from X to 0, 1, such that G and M Bn bar equals to 1, and then the complement of XBM is equal to 0. Okay. So the claim here is this is the countable collection we want. Okay. But to prove this, what do you need to do? I only define this for such special kind of Bn. Okay, but to prove that this work for all S0 and all U, what should I do? I need to check at every S0 and open set content U. Okay, I need to check whether it does the job at one. First of all, do you agree that this is countably many? Because it's just indexed by Z cross Z. Z cross Z is countable. Okay. So let's check that this can do what we want. So then it is clear that G and M is countable. Okay. So then we need to check the condition for given any S0 and any open set. Do we have such Fn such that it takes value greater than 0 at S0 and then take the value 0 at complement of U. So finally, given these two things, what can we see here? Okay, we can actually choose a basis element. Okay, S0 that contain S0 and contain in U. Okay, this is the basis condition, right? Okay, this is the basis condition. So using regularity here, so we are regular, there exists another open set containing S0 such that this V here is squished in between Bn and S0. Okay, such that a closure also squished between them. Make sense? This is an equivalent definition of regularity. But you have another open set. Okay, so you can squeeze another basis element. Okay, so and therefore there exists an N such that Bn is living inside V. Make sense? Okay. Does it make sense? Okay, I use the regularity to squish an open set into it, and then basis switch another basis element here. Topological basis. Because for every open set, there should have a basis element living inside it. Correct? Okay. But now, you see, just now our G and M, right, need what? A basis element with a closure of a basis element. But here, I only got basis element with another basis element. Can I squeeze a closure here? Out. Out. How to squeeze? Since Bn is in V, then the closure of Bn must live inside the closure of V. Make sense? Okay. So what do we get for all of these? S naught in Bn, living in V naught, living in Bn. Sense? Okay, so we have a Bn bar living in Bm now. So what should the G you need to use here? What is the G I need to use here? I just use G of N M. Okay, G of Nm is positive, in particular equals to 1, okay, at x naught, and vanishes outside Bm. Okay. But if you vanish outside Bm, meaning you vanish outside U. Make sense? Thousand. Make sense? Make sense or not? Huh? You think so? You understand? Huh? Not so sure. So the problem here is we create this condition here. Bn bar inside Bm. Bn bar inside Bm here. Okay, once we create this condition here, what can we make sure? We can make sure that everything in Bn bar. Okay, so how we construct this GN. So we can make sure that everything inside Bn bar I set to 1. Everything outside Bn is 0. Bn or Bm? I think it's Bm. Outside of Bm is 0. Okay? Because complement of open set is closed. So there are two closed set I can separate. Okay? So here I can send everything inside Bm bar to 1, outside Bm to 0. But you see, outside Bm, meaning it is also outside of U. Because U contain Bn. Right? Yeah? Bm, W. Right? Bm outside must contain U outside. Make sense? Okay. Okay, so there's only countably many functions we need here. Now, so we define this one. Okay, we define this function here. So what's this function here? Just now I got a lot of G and M, right? They are countable. So I relabel them 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? And I evaluate X using all these functions. And then give me a sequence of number. Make sense? Okay. Now, what do we need to show here? We need to show that it's continuous. Okay. And then we need to show that it's injective. And then we'll show that the inverse is continuous. It's a surjection, so it's subject on the image. I didn't say it's subject to the whole thing. It's subject to the image. Okay, this one no need to check anymore. So why is it continuous? So it is continuous because each f here is continuous. Okay, if you still remember how we construct continuous function, I just need to make sure that all the f is continuous, and then this is with a product topology. Okay, not the box topology. Remember last time I showed you an counter example. Okay, if it's box, then you cannot just say that, oh, every component is continuous, then the whole thing is continuous. So now you need to, so now first of all, so let's write down first, f is continuous because Rw has the product topology. Okay, and for every Fn here is continuous. Makes sense? Okay. Okay. Second, F is injective. Why is it injective? So injective meaning if Fix, let me think, injective is what? Fx equals to Fy implies x equals to y. In other words, if x not equals to y, then Fx not equals to Fy. Okay. So because if given x not equals to y, okay, what do we know here? Actually, we know that by T1 axiom here. Okay, so what do we know by T1 axiom? We know that there exists n such that Fnx greater than 0 and Fny equals to 0. Why? T1 says what? Singleton set are all closed set. So you can separate two of them. So one of the GNM will separate them. Okay, one of the GMM will separate them. Okay, then that GMM will tell you that the whole Fx is not equal to Fy. At least one spot you can separate them. At least one of the GNM will separate them. You understand? Huh? So GNM help you to separate all the point and a closed set. Separate one point and with all the closed set you separate. I don't know. So one point and one open set will define one GNM. So one of the GNM will separate them because we treat Y as a closed set. T1 says that every single thing is closed. Make sense? Okay, so what's the role of GNM here? It's really separating a point with all the closed sets. Yeah, makes sense. So there's one spot is different, then the whole function is different already. Okay, so injective, and then surject on the image. Finally, sorry, now on the proof will be slightly long for this theorem. Okay, it's not trivial anymore. So finally, one last thing we need to check. It's not too hard. Finally, we must prove that F inverse is continuous. Okay, so how to show F inverse is continuous? In other words, for every open set in X, we want to show that F of U is open in Fx. Okay, so if F is continuous, right, you look at the F inverse. Okay, but now you look at the F inverse inverse. So it becomes Fu. Okay. So how to show this? Let's do this. Okay, so in that case, we just pick one U, any U it will works. Okay, then inside this U, there's a point that's not in U. Okay, we want to show Fu is open, meaning what do we need to show? What do we need to show? If to show Fu is open, we want to show that Fu contains an open set. Okay, we show that U contains an open set. Okay. Okay, so let's take one point here, and then we will use this point to construct what's the open set contained in Fu. Okay, if we take a point here, then we map it across. Let's call it Z0. Okay, this Z0 here will live in Fu for sure, because it's an image U. Okay, then what should we do here? Then what should we do here? So note that there exists an n such that Fn of S0 greater than 0 and Fn of UC is 0. Okay, so this is a definition of F, capital F. Because UC is closed and then S naught is a point, then there should have some G and N that's separate. Make sense? Okay. So now we're going to use this information here to find what's W. I mean, the open set that contain in FU. Okay, we call it W. So now we're going to define W to be the pi n inverse of 0 to infinity. Okay, intersect with fx. Okay, so what's this pi n? Huh? What's the pi n here? What does it mean by pi n here? Pi n is the projection. Okay, so this projection go from where to where? Now let me define it for you. So this pi n here is a map from my R infinity to the how should I put this? R. But which part of R? So let's say here is um a bit illegal to write this down. Although it's illegal, let's do it still. Remember the last time we defined this using function. On. I project it to the AN copy. Okay, the N copy project. Make sense? Okay, and then I look at the pre-image. Pre-image. What the pre-image? How do you think? It's basically 0 to infinity on the N component, and then all the rest is R. Okay, and then intercept with fx. Make sense? Make sense? Make sense? Okay, I just take pre-image of this guy and then. Is it clear that this is open? It's a set of, what do you mean? I why are you asking? You're asking this, what's this set here? What's this set? So this set basically is at the AN component, you can take 0 to infinity, and then all the rest, free to take any element in R. So okay, how about let me write down what's this set equals to. So pi n inverse here would be R R R to the n component is this, and then R again. Make sense? Okay. Okay. Yeah. So you basically keep continue on. Yeah. Yeah. Okay, then take this intersect of fx. But this is open because what? Because pi n is continuous. Projection is continuous. So the pre-image is continuous. It's open. Okay, open. I mean pre-image of the open set is open, and then you intersect with this set here is a subspace topology, so it's open. Yes, so W is open here. One thing we need to see here. So the point here is we want to show that. What do you want to show? We want to show that what's left to show is to show that actually W live inside. Okay. Okay. Okay, makes sense. W is in FU here. Okay, it should at least make sense as the n at the n level, and the n level should be make sense. Why then? Because you already throw all the complement to 0, complement of U to 0, but it's not in your image either. It's not in your image, right? Because you are looking at the pre-image of no, not 0. I mean, you are not looking at the pre-image of 0. Okay, so this part for sure definitely not include U complement. Definitely, who is not including U complement? So here, so this part here, yeah. So you won't live in F of UC. No, no. Yeah, at least at the n level lah. I'm talking about at the n level. Okay, but in general, how to check? So we check different thing. Let me see. Okay. Well, I think there's few things we need to check, right? To show that it's open, we need to show that W is in here, but at the same time, this W should contain our Z0. Okay, because Z0 live inside FU just now. Okay. Right. So there are two things to check. So first, why is it Z0 in W? So we check that if we apply pi n to Z0, okay, and then I look at what happened, pi n applies to fx0, then this is just fn of x0. But in this case here, we know that this n we pick is strictly greater than 0. Okay, so this n here is specially chosen for S0. Okay, for S0 here. Okay, makes sense. Does it make sense? Does it make sense? What's S0 again? So S0, S0. Okay, S0 is just F applied to S0. Sorry. What are you asking? What is S0? Okay, so S0 is the point, yeah, a point in U. Yes, that's right. A point in U, yeah. Okay, a point in U. Yes, that's right. Yeah, point in U. Yes, and then you apply F to it, and then you get this Z0. Yeah, make sense? Okay. Okay. So Z0 will live inside W. You just need to check that it's in the pre-mesh of pi n of pre-mesh of pi n of 0 to infinity. But it is because if you evaluate it, the value of S0 should be greater than 0. So it's something in between 0 and 8. Okay. Definitely in fx, because this is how we define our Z0. Z0 is equals to f of S0. So it's inside fx. Okay? Okay. Okay. So how about next thing? So next, we want to show that W is in FU. And this is what we want to show next. All right. So this is a subset inclusion. Okay. So we need to check every point in W. Okay. So next, so for every Z in W. Okay. So what do we do? Then Z should be equals to Fx. Okay. For some X. Okay. Is it true? Because this is how we set our W, W must come from image. Okay, so there exists some X that realize this Z here. Okay, makes sense, huh? Okay, then we actually want to prove that this X come from the U. Okay, we need to prove that this X actually live in the U. Okay, so what other things we know here? Another thing we know here is the N projection of Z should live inside 0 to infinity, because W is the pre-image of this range. Right. So if we put these together, what do we have? So we have pi n of z, okay, equals to pi n of fx. Okay, so I project to my n component here, which is fn of x. Okay. But what is this? What is this here? What should this be? So pi n of z is fn of x. Okay. And what else we know here? Fn here will vanishes outside U. Okay. Fn vanish outside U, right? Just now we say f to the uc is 0. Okay. But just now we said that pi n of z live inside 0 to infinity. Does it vanish or not? Does this fnx vanish? No, right? Okay, so if it doesn't vanish, where should this point live? Complement of U, which is U. So the point x must live in U. Okay, so then z equals to fx, which is in fu. Long proof. Okay, you rarely see long proof, huh? If it is long, your lecturer already throw it away, right? 没有在内涵谁，我是在内涵全部。Okay, make sense, huh? Okay, yeah. I choose to present this proof is it's not very hard. Okay, it's trying to put everything you learn together, continuous function, and then complement, and countability. Yeah, so try to put all these ideas together. Okay. Okay. So from this definition, I mean from this proof, right? What we can say is actually we can say that a map f from x to y is an embedding. I think Moncrief used embedding, I think, but it's the same thing. If f is an injective, okay, continuous map, such that it is a homeomorphism on its image. Maybe you might think that, wow, so many adjectives, injective, continuous, such that it is homeomorphism on its image. 1, 2, 3, 3 things at least. Okay. But this is the thing that happens in real life, you know. You are an embedding into the R3. You are ejective, 对吗？不可能你的点跟那个，不可能 Lydia 的点跟 Adrian 的点有 intersection 嘛？你想一下有 intersection 发生什么事情？连体婴，对吧？不可能的嘛。Okay, so every individual is an embedding. Okay, it's injective, continuous 嘛？Lydia 你会不会 continuous？一节一节的。
这应该是 connected
对对对，对，可能可以不 connected, disconnected, okay? So continuous, such that it is homeomorphism on X image. It's homeomorphism, right? 你的皮肤是不是有时候会水肿啊？会哈，可能肿一点点。今天可能早晨比较看起来比较胖一点，昨天喝太多水。没有啊，现在瘦了，早晨瘦了，都是减肥是吧？最近好像不是，被他的医生 stress 到了。OK， 对吗 ？So it's a homeomorphism 哦，你是会变的，你是会变的，你自己本身你会变的 homeomorphism。OK， 你是一个会流动的。Okay, make sense so far? Okay, so example is what we had just now. The function that we defined from x to R infinity actually is an embedding. Okay. Embedding is very natural in our world, actually. Okay. So far, any question? No? No? How about we mention, okay, let's not mention. Okay, how about let's take a break. Let's break until 3:57.不能再打 project 啊。你先。OK，啊？是吗？因为我之前做这个。CS 好像影響到你發錯。啊，啊，是啊，成日都帶。不應該調寫，應該要把它 deadline 調。好像CS 幾分？招生交了沒？難怪你這樣寫吧。
因为我昨天晚上在那边打完了，我才开始看你的第二台。
不是。
那因为
放假就是刚来的吗？
几个礼拜前的。
3个月啊，一个星期来。这样快就1个月了，背后薪水都拿了。
不需要。
对。到期以前的挨个比分是挺好的。
哎，好像是我推给他。这三天还有个几天？
那发现好像是在知道。哦。没问他一般就是啊。
等下，还没给那边那个印的时候，那你就打开这个机槽，来个杯子来。
没有，我是
视频，因为我真是没有online收过很多，
收入很难，
然后给你出来的地方，
我都不懂他。对我的不是。
校正，你看我们刚才做了什么事情？
那改变了，不然你看等你看，
刚才画的是谁？
你的三天是新学的。
怎么那个？
哎，那我把它想成什么一开始？哎，可以把它想成那个原神那个元素方格。元素。
这个东西叫做吹上去。
为什么？
好吧，吹起来。
并且
这看起来像是一个 3D 的本，这是一个 3D 的dimension，然后在 D dimension 上面你画一个圆，然后这个是方式，然后这个
啊，就是我们把这两条线吹起来。
哦，要不然对，
垂直啊。
是啊，
然后把两个东西吹成这个。
哦，你呢？
然后还切不切是为法对。
他讲到这个草，就点到分了。
对，这个才有分都。然后以后我们做assignment的时候，没有不要再写，一开始画这种东西下去。
哎，那个零哦，我这上不是从这个
不可以毕业掉，
这样啊，
一样啊，掉，
我已经把你接了，我不管。
一样啊，掉，他已经其他的停止待着，这样啊，掉。就是这种高的 base 的那个 acknowledgement 一定要拿掉，那一不会放这个进去，
不是放原本对吧？
对啊，因为你放这个，它就会被 scan 到了。
这么死啊！
老师，我还是搞不懂
哪个
这个 sounds like
Urysohn 啊？
function 为什么是 continuous？
哦，为什么它的 function 是 continuous？你看，
所以假设说你 define open process in
对
between with rational index 啊，
然后
但是那个 index 本身它不是，
对，没有错，没有错，没有错，没有错，
人为什么把
拿到 rational number。
correct 到一个
Like OK， 等一下先来，so well I mean like，给我想一下，没有，我们的 claim 是这样，OK，你知道 like，so first of all 这个 fraction 是 dense in real number，知道这个什么意思吗？
fraction 是 dense in real number，
呀，这一个 set of
okay,
fraction，
Q is dense in real number，
对，意思说你可以拿到 irrational number 用这些 fraction 哦，OK 吧 ？make sense 吗
OK，
？make sense 啊？
我上次应该是没有听懂怎样
对
叫 rational converge。
Well, I mean， 如果是 rational 比较容易讨论啊，你就拿那个 decimal expansion 的 truncation。把这个 dyadic 的方法是，
你的分
对 two power n， 但是它不远，其实它不远，因为 two power n 的意思是什么哈？你把你的 space chop 成1/2、1/4、1/8、1/16这样子 chop， 你一定是可以找到越来越近。我们的 decimal expansion，OK， 假设从 decimal expansion 的 truncation 开始想啊，可能你0.6嘛，0.6不是跟1/2蛮靠近吗？然后你再看下一个1/8，它跟哪一个1/8靠近哦，然后你就可以来 try to approximate
OK，so
rational number， yeah，
我不懂
这样，
我不懂 number theory 有没有这样的 theorem，
你讲
就是 any fraction， 你可以把它写成power of 2 的 denominator 的 fractions 的 sum。
对，喂，不能吧？能吗？
因为你刚刚你那个意思是它比较靠近哪一个power of 2 的 denominator 的 fraction 嘛？比较靠近哪一个
binary 哦，我想一下，讲 binary 哈。可是 binary 是24嘛，这个是反方向的 binary， 懂什么意思吗？因为 binary 我们是在指 positive integer 嘛，因为是1 square 是，对吗？1 2 and then 4 8， 不对吧？4 to 5，但是这个是反着来嘛，呀，算是 binary 了，算是 binary， 呀，算是 binary， 懂什么意思吗？
对啊，
就是 like
OK， so 比如说
0.6嘛，
比如说1/3啦，
呀，
我可以把1/3写成一个
1/2，
一个 infinite sum of 这个 base 里，
可以，infinite sum，
然后
但是你的 infinite sum maybe 它可能会 convert， 所以可能后面都是这样的。
明白。
如果不能，你就继续了，
就加到一点，
加吧，它会 convert 呀。
OK， 这样如果这个可行的话，那就可以 make sense 啊。因为比如说，
对，
因为比如说有些分母是 require 不同的 primes 的话 ，at least 以这个1/3作为 example， 我可以写成一个 sum， then 其他的 primes 我也可以写成一个
yeah，有想象。但是你那个是3哦，呀，但是我现在是看的是 sequence 啊，所以是你的3过后，然后你就 sequence of 3哦，它会 convert。OK，
谢谢。
OK，
老师，
免得很累。
不是摇头，摇你的臀。
对。
啊， 不会啊，
我累。
没有我饿。
还有一个钟。
哎呦，你的
哎，你有快放到那个塞的。
Hello, testing. Okay, let's resume. So we can quickly finish, quickly go to dinner, quickly submit your assignment. Okay. So there's something that I don't want to go in detail. So first thing is Higgs extension theorem. So if you have a normal space and then you have a closed subspace, so any continuous map from this closed subspace to a closed interval could be extended to a continuous map of all x. Okay. So you should think of our Urysohn lemma. Okay, you have a closed set and then you extend to a whole space x here. But if you go and look for this proof, actually it uses uniform continuity. Yeah, sorry, uniform convergence. Okay, uniform convergence to prove this. And then once you can map to a closed interval, then you can map to the whole R. Okay, so meaning if you have a continuous map on a closed subspace, right? Actually, you can extend it to the whole space. Okay, this is a Higgs extension theorem. This is quite important in real life actually also. Think of that you have a data that you know that is closed, okay? And then you know that there's a continuous function that map from this data to another space, okay? Real number in this case, just real number. Okay, meaning maybe you evaluate some number, linear function like that. Then maybe your boss asks you, hey, we know this data, can we expand it to general situation or not? Can we put in more criteria or not? Can we extend it? So if you know that the whole space is a topological space which is normal, and then the data you have is a closed set, then this theorem tells you that it is possible, okay, to extend it as a continuous function, okay, to the whole screen. Okay. Does this proof tell you how to extend? Let me see. Does this proof tell you how to extend? Construct a sequence of xn defined blah 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 blah. Oh, actually, let me see. Yeah, it did. Okay, it did. Okay, it did tell you how to extend it. Yeah, I think it did. Okay. Okay, this proof is quite constructive. So if one day you need it, maybe you can go and look for this proof. Yeah, this proof, I think it tells you how to extend. I put a summary here. It's a proof sketch. Hopefully can help you to understand the textbook proof. Okay, the textbook proof is even longer. I think a few pages. And very technical actually. And then it uses uniform, yeah, it uses geometric series. Okay, so you need Weierstrass M test to test it. If you still remember from your MA. Okay, which I won't go through it. Okay, once you can have a function to a closed interval, right? It's really easy to extend it to real number already. Okay, there's a homeomorphism there. Okay, and then there's some more metrization theorem, which we won't pursue, but maybe it's interesting to look at. So one is just now we showed that every second countable regular space is metrizable. But let's say if you only is regular and your basis is countably locally finite. What's countably locally finite? So locally here meaning something to do with every point. Oh, yeah. Okay. So what's the countably locally finite here? So let's talk about locally finite. So a collection of a subset is said to be locally finite in X if for every X in X, there's this open U that contains this X. Yeah.
It's coming in for like 1 year.
Awesome.
大的不清楚。OK，
还有吗？拜拜。Okay, so locally finite here says that if you take wait so you have a collection of subset of x, right? Okay, you have a collection of subset, right? So you have a x and then subset of x. This collection is called locally finite if for every x, every x in your space, take an open set on your x. And then this open set only intersect finitely many elements of A. You understand what I say? So let me draw this picture here. So let's say your x is like this. Okay. And then the collection A maybe got A1, A2, A3, A4, A5, A6, something like that. This set could be infinite, okay? But the point here is if you take a point from this space and then you take that exists, okay, just need one, okay, just need one U such that it contains X and intersect the collection of A finitely. Okay, here finitely, no? How many of them are? 1, 2, 3, 4, 5, 6. Okay, this has to be true for all points. Then this red one, the collection of red circle here is called locally finite. Make sense? So this finite refers to the finite intersection. Okay, so how about countably? Countably means that if this collection A can be written as countable union of locally finite collection. What does this mean? Countable union of this kind of set. Meaning this countably locally finite should have more element than locally finite collection. Because maybe this A couldn't be locally finite. But if you put enough locally finite collection into it, it becomes locally finite. Is it? 可以这样讲吗? Yeah, 可以这样讲, I think. Okay. You put enough locally finite collection into it, then you can have this property. Make sense? Huh? No. I think I cannot say like that. It's just that, yeah, just write that as a locally finite. Wait a minute. Countably union of locally finite collection. So, let me think.
So for example,
Yeah. So for example,
collection A is locally finite.
Mm.
It must be countably locally.
Yes, it must be countably. Yes, that's right. Yes, that's right. That's right. That's right. That's right.
And then,
Let me think. So okay. So locally finite implies countably locally finite, right? How about countably locally finite? Is it possible that it is countably finite but countably locally finite but not locally finite? No. But
written as countable union of finite collection. Then it must include.
But this already locally finite, right? All these AN, right? Yeah. Let me think. What could happen here? So it could be a case that you could intersect infinitely many set from different AN, but for each AN you will only intersect finitely many. You understand what I said? You understand what I said? Can you imagine what I said? So it could be the case that you intersect different AN infinitely many, but you will always intersect one of the AN finitely many. Make sense? Make sense of what I say? 可以懂我讲话吗？你可能 intersect 不同的 AN， 但是否每一个 AN 你都 intersect finitely many？ 因为它每一个都是 finite locally finite，但是可能你这个 open set 会 intersect 所有的 A， 但是可能你就不 finite。如果你单看一个 AM 的时候，它肯定是 finite。OK OK，so 很特别哦。你看，我们把那个second countable 的 property 啊，降到这样子的东西 countably locally finite。像上次嘛，还记得上次嘛？我们要 equate path connectedness and connectedness 的时候，我们做什么啊？我们加了一个东西叫做 locally connected，我们加一个 locally。我降了这个过后变成一分 only 一分。So this is a Nagata Smirnov metrization theorem. I guess these two guys, one is Japanese. The other guy, is it Russian? Maybe. Okay, and then this Smirnov continue with metrization theorem. 很想要 metrize topology space. So a space is metrizable if only if it is paracompact. Okay, Hausdorff, that is locally metrizable. So what are all these? So what's paracompact? So compact, you know, right? You can compare every open cover. So what's paracompact then? If every open covering A here has a locally finite open refinement, has a locally finite open refinement that covers X. Locally finite, I introduced you just now already. So there exists an open set that intersects this that is finitely many. But what's refinement? Refinement says that for every B in B, there exists an A that contains B. So this refinement is you might not take the covering from A. It's not subcover. It's just that it's like Riemann sum, you know, Riemann sum, refinement. Do you remember refinement of Riemann sum? So you got the rectangle, right? The rectangle chopped in half, right? Okay, so here not chopped in half, right? You just take some subset. Okay, subset of the element in A. Refine it. Okay. You are not taking subcover, not exactly the sub collection. You just from the element in A, you pick some subset out of it. 变小一点。Okay, refine. Make sense 吗？对吗 ？Refine. If you want to refine the gem， 你也是把石头丢掉嘛，你拿少部分出来嘛。那钻石是小的部分，所以这么贵，对吧 ？And you refine it. And then this set of things have to be locally finite, okay, the intersection property. And then cover X. Union of them will cover X. 就是刚才我画的啦，它会 cover 完这个 X， 然后有 locally finite property. Then this is called paracompact. And locally metrizable, if for every point X in X has a neighborhood that is metrizable in the subspace topology. So it just says that at every point you have a neighborhood that can be metrizable. Then your whole space can metrizable. Can you imagine what is going on here? Can you imagine? 可以想象嘛，这两个怎样冲在一起啊？I mean 三个 actually, paracompact, Hausdorff, and then locally metrizable. Then 你要把整个 space 都 metrize， 可以想象嘛？我现在是局部 metrizable， 怎样变成 globally metrizable？ through compactness, paracompact, through Hausdorff. Hausdorff 说什么？两个点 you can use two opposite to separate them。又要在一起，又要分开，真的是难分难吃。好，又要把它包紧紧，又要把它分开。这样就可以 metrizable。所以你们的爱情是可以测量。OK OK, yeah. So I think this proof is quite technical, so we won't prove it. Okay. Yes. 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 What do I mean by what? Oh, okay. So we degrade the second countability, is it? Degrading the second countability to get metrizable. Yeah, that's what you want to say. Last one. Okay. So previously, what we have shown is regular plus second countable. We got metrizable. Second countable means what? Countable basis. But now it's regular plus the basis which is countably locally finite. That's it. Okay. A basis which is countably locally finite. Previous is countable basis. Countable basis just says that, oh, I just need countable of them to build this basis. But now it doesn't say this basis is countable. But what it says is this basis is countably locally finite, meaning you can write it as a countable union. Not countably many, it's countably union or locally finite collection. Okay. Locally finite collection is this finite intersection property there. Okay. This countably union might not be countable all the things, is it? Yeah, might not be. Might be or not. Might not be, right? Might not be. Because this collection could be uncountable. Who knows? 对吗？这个东西可能很大的嘛。Yeah. It's just that this union is countable. Okay, it could be a countable union of uncountable thing. 不知道。Make sense? Okay, ma. So I think, yeah, maybe the way I use the degrade here maybe is slightly misleading, but yeah, maybe slightly misleading. I'm not sure it's upgrade or downgrade. Yeah. But we change the second countable property, and then we get a biconditional segment. I would say these guys are very, very brave. I think very brave because I actually don't know how to imagine this thing. I don't know how on earth they can come up with this idea. I don't know. I don't know how to imagine this thing. I don't have a very good intuition here. Yeah. And we never learned this in our undergrad actually. It's because I need to teach you guys, so that's why I learned it. Yeah, we never thought about this like by our lecture. This is not going to pursue. Okay. I don't know how they imagine this. Yeah. By the way, I will introduce you a book. I think I forget to upload yet. Counter examples for topology. Okay, in that book, there's like 100 of counter examples. And then that book will tell you every counter example is T0, T1, T2, T3, T3.5, T4. There's some other thing called T2.5. I just saw it. And then it would prove whether it's compared or not, connected or not. It didn't prove that, but it tells you. Okay, maybe it's easy to check. Compare or not, locally compare or not, connected or not, locally connected or not, or para-compare or not. There's a different way of compactness. There are different way of connectedness. Okay, the list out the table. Okay, you can. Yeah. Okay, so far, so good. What time is it? 4:16. Okay. Okay, we can at least cover one major theorem today. So next theorem I'm gonna present is called the Tikhonov theorem. So we have enough thing to do Tikhonov theorem now. So let's tell you what's Tikhonov theorem first, and then we will do the preparation. So what's Tikhonov theorem here? So basically it says that a product of compact topological space not just is compact, we can go both ways. How should I put this at? A product is compact if and only if xi or xi are compact. Okay, So last time we only proved for finite case. Okay. Now it's actually true for the infinite case here. So infinite case here a bit tricky, a bit tricky. But here we will use the product topology. Okay, we'll prove this. So two key things to prove here, to use here is, one of them is called Zohn's lemma. I'm not sure you still remember or not. So Zohn's lemma is if you have a partially ordered set, okay, it's a non-empty partially ordered set, then every chain, okay, or in other words, every totally ordered subset, and if this chain here has an upper bound in X, then X will has a maximum element. Okay. How is it equivalent to AOC? Huh? Okay, I think last time I proved it. I don't know, I didn't prove it. I post a note on the equivalent statement of AOC inside when we do AOC. I think inside there there's a proof. Yeah. And this proof actually is quite technical, but I didn't like remember what's the main point there. Okay, so this is a proof by AOC. Axiom of choice. Okay. All right. Okay. So before proving Tikhonov theorem, we need to prove this theorem. So okay, wait. By the way, before that, so do you know what's the significance of Zohn's lemma here? So you got the upper bound, right? Upper bound, and then the point here is X has a maximum element. Do you still remember what's maximum element? Anyone take combinatorics this sem? What's maximum element? Huh? Every other thing should be less than or equal to this guy. Is it maximum? No. What's the definition? Huh? Why I say definition? Actually, there are two things you need to take care of. One of them is upper bound, one is maximum. These two are slightly different. Huh? No element greater than it. Uh-huh. Yeah. 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 Or either not comparable, either or less than equal. Okay. Yeah. There's another, what's the other concept? Very similar to maximum. Okay. What's upper bound?
Everything is comparable.
Oh. Okay, so that's only for totally ordered set.
Yeah.
Okay. Okay. So maximum could be like a hill, you can think of it. Okay, you cannot compare one mountain with the other mountain, but every mountain should have a peak. That's a maximum. Okay. Good. So let's prove this. Alexander subspace theorem. Okay, this subspace theorem is quite famous actually. Although I will also first learn here. Alexander subspace theorem. So consider a topological space with subspace, so subbases. Okay, still remember what subbases is? So your topology is generated by union of finite intersection. Okay. Then X is compact. Wow. If and only if every open cover of X by subbasis element from X has a finite subcover. Last time actually we proved this for basis. Basis is quite simple, but it turns out that For subbases, it's quite complicated. Okay, until we need to use zones level. It's not that easy when we move to subbases. Yeah. Then I'm not sure whether this is true or not. Okay. Anyway. Okay. But do you agree that this statement is naturally you will think about it? Do you naturally think about it? So if compared, every open cover have a finite subcover, right? So now so last time we reduced to bases. Now I reduce again to subbases. But turns out that this is quite hard. So that's why this theorem bears a name. Okay. Okay, so one direction actually easy. Which direction? Which direction, Zhaosen? Left to right, why? Hello, Yao Zhaosen. 给招生机会一下，没有，他们全部在做 project，可以，肯定啊，你又给我看。This one is open cover by subbases. Your open cover is by random open set. So subbases is also open. Okay, so there's a finite subcover. Okay, good. Okay, so one direction is easy. Okay, how about the other direction? So the other direction we will argue by contradiction. Okay, so how to contradict it? So we suppose that every open cover of X by subbasis set has a finite subcover. Okay, from X here has a finite subcover, but X is not compact. Okay, so meaning what does this statement trying to tell you? If I use subbases to cover, I can find finite subcover, but random open set, I cannot do that. We need to cook out a contradiction here. Okay, we need to cook out a contradiction here. All right, so in this case, we just play with a negation of compactness. Negation of compactness says what? Let O be the collection of open cover such that it doesn't have a finite subcover. Well, there's ordering here, right? Okay, we can order these subset. So they are partially ordered. Okay, partially ordered by set inclusion. Okay, why is it partially ordered? So you might think that some of the subset are not comparable. Okay, not comparable doesn't mean that their intersection is empty, or maybe it's just that it's not fully living in each other. Okay. Yeah. All right. But anyway, we can still pick out a chain. Okay, let's pick out a chain. So let OI be a totally ordered subset. So meaning we pick a chain of them that can be a subset all along the way. Yeah? 什么？有没有可能你 pick 不出来哈？我想一下有没有可能你 pick 不出来哈？你 pick 不出来。It could 我想一下，可能 pick 不出来。If 你 pick 不出来 ，maybe is a finite subcover 嘞，对吗？会不会这样子 ？If 你 pick 不出来呀，有可能吗？可能 empty 吗？啊 ？Is it possible to be empty here?
Zero finite.
Is zero finite? What do you mean? 中国有 zero 在这边。Is it possible empty? This guy. if I cannot totally overlook them. Is it possibly empty, huh? I think. Huh? Sorry?
For every chain.
Ah, okay. Yeah, makes sense. Makes sense. Okay, so let's see what we're gonna do with this thing. Okay, maybe empty also work. Okay, maybe empty also work. So let's try this. So let's continue first, see empty will cause problem or not. So suppose we have this chain here, then for all j in I, okay, what we could notice here is all j here for sure should be living inside the union of all these guys. This one is for sure because one of the OJ is inside the union. So actually M is the upper bound, okay, or the possible upper bound of. Okay. So you got a chain, right? Okay, or 1, or 2, let's say maybe, for example, O1, O2, O3, and then blah blah blah. Right. But at the end, you attach one union. Okay, if we can argue that M is in all here, sorry, yeah, M is in all, which in particular, oh yeah, M is in all, then we can use Zone's lemma here. Okay, that exists a maximal element. Okay. Sorry, let me see. Yeah, it's a O. Wait, let me think. You mean the upper bound for OI? Yeah, I think so. Let me check this. Everywhere has your upper bound. Yeah, sure. Okay, good. It's what this. Okay. Okay. So then, if we can argue that this upper bound here live inside the original O here, so original O is a collection of open cover which do not have finite subcover, then Zone's lemma will apply. Okay. Does it cover X or not? So does it cover X? Does it cover X? Let me see. Does it cover X? Okay. Hey, there's something you want to note here. This is a collection of open cover. What does this mean? This is not a collection of open set. Do you know what's the difference? Collection of open set and collection of open cover. Open cover is a collection of open set. So actually, this is a collection of collection. Collection of open set. So this is a collection of collection, okay? So the OI here is served by already covered by X. Make sense? Make sense? 可以听得懂吗 ？OK， 什么？什么？好的 it is okay. So all these OI itself is an open cover. Meaning what? It is a collection of open set that cover X. Okay, so for example, let's say I can write OI as a union of, let's say, J such that OJ like that. Okay, and then this union will contain X or equal X actually. Okay, make sense? And then this little O, or not little O, but no script O here is an open set. Make sense? Yes, 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 exactly. Because it's a collection of open cover of X. A lot of open cover. Open cover means a collection of open set that cover. Okay? Happy? Okay. So the union you do here, what is this? The union of open cover obviously is still an open cover. One of them already cover X already. You union everything that can cover this X. Okay. So still cover X. So first, obviously, it is not obvious if you don't understand that, but after you understand, become obvious, then it can what? No, I want to show that M is inside. M is in O. Inside O. The zone's lemma. This upper bound here must be stay inside X. No, I'm arguing the upper bound is in O. That's it. O is a collection of open cover. So I want my upper bound to stay inside O. So meaning it has to be an open cover. Okay, so first thing I show that it is an open cover. Second thing I show that it do not have a subcover. Okay, so that it stay inside O. Make sense? Okay. Okay, understand what my goal here? Okay, I want to show that this upper bound here stay inside O so that I can fulfill zone's lemma and then find out the maximum element and then continue. Okay, so to show that the upper bound live inside O here, I need to show that it is an open cover, and then this open cover does not have a finite subcover. Two things I need to show. Okay, first thing, it is open cover because it's just union of open cover. One of the open cover already enough to cover your X, but I union everything together. Okay, then next thing I want to argue to you is it do not have a finite subcover. Okay, this one I need to prove to you so that I can show that this upper bound live inside this collection. All right, make sense? Make sense? I want to show that it live inside this set here. Okay, this set here is open cover. And then this open cover does not have finite subcover. Two things. Okay, first thing I show you, it is open cover already. Second thing, I need to show you that it does not have a finite subcover. Make sense? Okay. So suppose on the contrary that M has a finite subcover. Okay, see if we get contradiction or not. Okay, suppose that it has a finite subcover. Let's call it U1 blah 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 up to UN or in here. Okay. Then this UI, right, should come from some OI. Okay, so let's say there exists IK in J such that UK come from some OIK. Okay, make sense? Make sense, ma? Because my mu are just union of all these open cover, ma. Then the finite subcover obviously come from some OIK lah. Okay, but the key here is here. Here is the key. Okay, 钥匙在这边。Since IK is finite, since IK is finite, and OIK is totally ordered. What does it mean? OIK is totally ordered. So it form a chain. It form a chain. This OI form a chain. 越来越大 maybe. 越来越大. And then where is your UK? Your UK live in some of them. 看得到什么东西吗？看得到什么东西吗？看得到吗？ If you consider all these UIK, what happened? What happened? This UI, U1 up to UN should live in some big U, some big O, OM here. 对吗? It should live in some big OM. But what happened? OM is an open cover. We like subcover, but I found you a finite subcover. Okay, so this contradicts that OM has no finite subcover. Okay, so this is a very clever move on the totally ordered set. Okay, this will order our sub collection here nicely. Okay, make sense? Okay, ma? Okay, so then thus mu is in O, and Zone's lemma will tell us that there are maximal elements. Is that O has a okay, good. So what's the next thing we want to show? 一般都忘记要做什么。contradiction 啊。还没有用到 sub basis， good， very good。我们还没有用到 sub basis， 我们要用了。对，我们要用了。Okay, so now, now this maximal element live inside our O, right? Now this set here, we will do contradiction based on this maximal element. Okay, this A here is an open cover without finite subcover. Okay. So what we're gonna see here is, let's say we take our script A here, okay, intersect with our subbasis. We also know that subbasis is a union of subbasis element to be X, right? So this two intersection is holding. Okay. But let's write down. Okay. So let's say this is what I meant here. So a bit of abuse notation. Although open cover, we say that it's a collection of open set, but okay, sometimes we view it as a union. Okay, a bit of abuse notation here. Okay, so this two intersection looks like this. Okay, agree? Okay. So let's say if this were covered X as a cover of X by sub basis elements, then it would have a finite subcover. Which contradiction to A having no finite subcollection. Sorry, finite subcollection that cover X. Okay, so because we assume that every covering by sub basis element must have finite subcover. So if this is obviously covering by basis element, so if it cover X, it must have finite subcover. But if you doesn't want it to be true, that means this intersection cannot be X, cannot cover X. Okay, so the only possible case is this script A here intersect X does not cover X. If it cover X, then you have a finite subcover already. Yeah. Okay, let's think about it. So let's see. Let's think about it. So if A intersect X cover X as a cover X by a finite subcover basis element, it would have a finite subcover. And this have no finite subcover. I think.
Oh, sorry.
What do you know? Yep. Yep. Yeah, and then that thing that also mean that set cover X because the whole yeah. Okay. You can use this finite subcovering here imply that A has a finite subcover. Okay. Okay. It's just because you are how to go from intersection to original set. Actually, you are getting larger set, right? Because intersection you become smaller. And then intersection can cover X already. Then you throw away more restriction, then the larger set should also cover the N. Okay, so then only case is this thing doesn't cover X. Okay, then we draw contradiction here. So if it doesn't cover X means what? You can find something outside. So if this doesn't cover X, then there's something that live outside the complement of all the B such that B is in the intersection of A's intersect C. A intersect X. Okay, there's something inside this intersection. So now, there exists a U in A such that X is in U, correct or not? Because A is an open cover. Okay, so definitely you can cover this point here. And since S is a subbasis, it's a subbasis, right? So meaning what? This X here should also contain in some finite intersection. Okay, so this X 有两个物质现在。OK， 一个是 A 的物质，一个是 intersection of X 的物质里面。Okay, but we find this subbasis such that this intersection live inside U. Okay, so it's like how to say, S is finer than this A here. Can I say finer here? Smaller. Okay. Since X was not covered by the intersection, what does this mean here? Okay, so this actually means that we have one of the xi is not in A. Oh, sorry. We have all the I not in A. 看下有没有很奇怪这个东西。If X was not covered by A intersect X, then we have all the I here not living in A. Make sense? Does it make sense? We have all the I are not living in A. Make sense? Does it make sense? Since S was not covered by this, and then we have Xi not in A. Oh,
Yeah, because if I in A,
then
X is in S, I is in A intersection.
Like Adrian. Adrian, 快点 Adrian， 快点，最后10分钟嘛，快点 Adrian， 快点，快点。对 人合理吗？
可以。
Okay, if it live in one of the xi, right, because x already live in the intersection, so then x will live in both intersection of x and a. No? Okay, so for any j in this range here 1 to n, a union sj is actually an open cover of x. Okay, why? Because a already cover x. I just add in one of the xi. Okay, but see, where's the magic here? So where's the magic here? So this one is obviously true because a itself already cover. Just that I adjoin one more xi in. Okay, I just adjoin one more xi in, and then we try to draw contradiction here. Already covering x. Okay, and then second thing, by the maximality, okay, maximality of a. Because a already cover. A itself already cover. I just adjoin a new thing to it. Okay, so we try to do contradiction here. So by the maximality of a in O, what does this mean here? This is the largest open set that doesn't have a finite subcover. I build an even larger one. So meaning what? A union Sj must has a finite subcover. Because A is the largest that doesn't have finite subcover. Now I make an even larger one. This guy should be having finite subcover. So let's call it a name. So this finite subcover, we'll name it as Aij union Sj. Let's say from where? From 1 equals 1, I equals to 1 to nj. Does it make sense what I wrote here? So I labeled this AI here. How do I pick this AI? Depend on j. Okay, depend on what j I join here. Okay, and then union with nj. And then this is finite. So this nj here depend on this j. S1 maybe got different j, S2 got different j, N2, N3 got S3 got different N3. And then this AI are chosen based on what I adjoin here. Maybe S1 is a different choice, S2 is a different choice, S3 is a different. 很多 choice 在这边啊。Okay, so now what happened here? Let's see. Now, what we are doing here, very 很大件事情. Let's see. So first of all, we see that X actually live in this big set here. So what we're going to do is we union from 1 to nj of aij of xj. Okay, just now the finite subcover here, I union them together, 把它加起来. And then, 哪个来？我哪里有逗号？ union 有什么问题？union 有什么问题啊？union 有什么？没有问题啊，不是？我就把它加在一起吧。等一下我有用到，我就把它加在一起吧。I mean like 有什么问题？不是有什么东西我不可以 union 的？我可以 union 那有什么问题？对，没有错。但是 SJ 是那一个 set 里面的一个 element 呢，所以我可以加在一起。不是啊，这个是个 finite subcover 啊。finite subcover 的意思是说 these are open set 啊。我把两个 open set union 在一起，不是 open set。我在 S 是哪个 S？ 那个大 S。肯定啊，因为 SJ 是个 subbasis 的。为什么不合在 ？SJ is a subbasis element。
这个union一定活在 A 里面。
element 啊，你说 as an element 啊？
对啊，一定活在那个 A。
我在里面啊。啊 ？Like 活啊，你看，I mean 活的意思是什么？来，这个里面 OK，这个里面可能有 A1、A2什么含不啷嘛，对不对？那你 union of Xij 的话，你不是就嗯，我想一下哈，嗯，想一下啊，如果这个 union 了，我不是就是合在一起，对不对？哦，对哦，为什么？我不是要逗号吧？这里还是我有什么东西做错？我想一下，我要的好像是这一个东西耶，我想一下，所以我怎样要它呢？啊，你说这个啊，这个写在外面，这个写在外面的，这样子，这样 SJ 上面什么意思？这样子，想一下，嗯，这个意思是什么意思啊？我想想，喂，这个意思是什么意思啊？这个意思是什么意思？
这个意思就是左边那个 PAR 再加一个 SJ。
想想，
我现在看你 set 那点，
嗯嗯嗯嗯嗯嗯嗯嗯嗯，
对我来讲，这个跟刚刚
这个跟我写的就是一样的东西啊。这样的话，OK，I think I guess maybe the confusion is this one finite star cover. Is it the confusion is finite star cover here? Because because these are not the element coming from here. Okay, but let's say this has a finite star cover, then I can build this thing out. It makes sense or not? Because maybe finitely many of them will cover, but then I just consider them union SJ, then for sure this thing also cover. So I think the confusion is here, right? So let's say you have a finite subcover coming up here. Then the following, okay, maybe I shouldn't call them a finite subcover. Okay, let's repeat what I do just now. Then this thing also cover the following set also cover X. This one happy or not? Happy, huh? Okay, I think I also happier. Because if you pick finite subcover, they don't have union, right? But obviously, if you have finitely many of them already covered it, you attach Xj to all of them. Okay, so meaning this subcover is not exactly coming from here, but it's a consequence. Okay, huh? Yeah. I just take the finite subcover here and then adjoin Xj again. Okay, maybe you might think, oh, so 怎么做这样多事情? Okay, so let's say I can do this. I union them is X. I intersect all such thing is also X. OK，每一个 SJ 我都给它 intersect 起来，每一个我都打得到 X，每一个我 intersect 起来也可以拿到 X。Then we will use set theory here. Okay, so the important set theory you need to consider here is A union B intersect C union D is a subset of A union C. Wait, did I write something wrong? So it's living in A intersect C union B intersect D. Not equal, just subset. So using this logic here, we can see that this is actually living in the union of J from 1 to n of union, because we need to see this as a one thing, this Sj as a one thing, right? Because we can split like that, because Sj is not dependent on I. Okay, so then we'll split into this. Okay, but a very magical thing is we know this guy, intersection of SI here. What's this guy here? This guy here is just U. Union U. So what have we done here? U. So what is this? You countably union, finite union or finite union, and then plus one thing is finite. Okay, so this is a finite subcover of X from A. Okay. Which contradict A is it? Okay. Okay. So just now this U is come from AI, don't forget. And then all these AI come from A. Okay. So it's a finite union thing come from A. Okay. So a very important question before we break. So is it possible that this OI can be empty? Don't think about it. We can talk about it again next week. Is it possible that this OI here empty? Yeah, think about it. Okay, try to think about it. Does it matter or not? I mean, maybe you cannot find the chain, right?
That's the one.
Hey, one element is also a chain, wait. It's always not empty. Oh, okay. Okay, case closed. Okay, see you next week. One element say also a chain. Okay. 不然你讲吧。